So this is actually pulled from the notes that I posted a couple days ago, and what we're going to focus our attention on is this sort of, you think of these two words. If I say that I have a strong acid, that actually has a really important and specific meaning for chemists versus concentration, right? Concentration we've been talking about as molarity, and we know that molarity is the number of moles over the number of liters, right? And we've been using brackets to indicate molarity. But if I say that something is a strong acid or a strong base, that has a very specific meaning. And I've got my list of strong acids. That's what SA stands for, and SB stands for strong base. So I'll write that down here. So if we ever encounter a strong acid or a strong base, that word strong means something very specific. I'll use HCl as an example, right? HCl, acids have that typical H hanging out in front of it because giving off that H, that's the acid behavior. So strong acids are going to basically be a one direction type of reaction. All right, notice that this doesn't look reversible. It looks like it goes from the left to the right. And that's because strong acids and strong bases, what they do is they completely dissociate. And that means that all of the HCl is going to always break apart into H plus and Cl minus if it is in aqueous solution. So you never have any doubt. If it's a strong acid or a strong base, if I say that the concentration of HCl, let's say that it is a 0.5 molar concentration for HCl, then there's no doubt in your mind that when I have 0.5 molar HCl, that's going to make 0.5 molar H plus and 0.5 molar C minus, because that's what strong acids and strong bases do. They always disassociate. They break apart, and the concentration is really easy to find, okay? Now, the only tricky part here is if we talk about a strong base. So the strong acids that we'll worry about, and there are a couple others, but just for the sake of time, these will be the four that we focus on. So if we ever see HCl, nitric acid, sulfuric acid, or hydrobromic acid, you're always going to know that they break completely apart. Strong bases are all the hydroxides of group 1. So you'd have to look at the periodic table and figure out who group 1 is. It's everybody except for hydrogen. And then these guys. All right, so these are the strong bases. And the only tricky part here is if I'm talking about, say, let's do NaOH, and I know I'm off the screen there, so let me scooch this up just a little bit. So let's say that I'm talking about NaOH. Because it is a strong base, I'm going to put it in water, and it is going to completely dissociate into Na and OH minus, aqueous, aqueous. And so if I made up a value, if I said that this was a 0.1 molar solution, if that was the concentration, I know that that would break apart and make me a 0.1 molar concentration of Na and a 0.1 molar concentration of OH, because for every NaOH that breaks apart, here's the Na, right? Here's an O attached to an H. Every time I put that in water, I get one of these guys, and I get one of these guys, all right? Now, if I have one of these, right, Stella, I'm gonna put you on the spot here. Instead of getting one hydroxide when this guy breaks apart, how many hydroxides do we see in these ones?
2.
Yeah, so what we would do there is, and let me see if I can kind of squeeze just enough paper on there to show you. So let's say that the one that we were looking at was that last one, strontium hydroxide. So if I had strontium hydroxide in water, all right, it's going to completely break apart, and it's going to give me one strontium ion, but it's going to give me twice as many hydroxides. So if I ask you that for the concentration, it is a little bit tricky. So if I have a 0.1 molar concentration of strontium hydroxide, and I say, well, what's the concentration of the strontium ion? Well, it's a one-to-one relationship. For every one of these, I get one of these. So the concentration would be the same as I had at the beginning. But because I'm getting twice as much of this, I'm going to take a wild stab at what the concentration would be for the hydroxide there. That too.
Would it be 1.1, 0.1 m squared or?
Squared's not a bad guess, but it's even simpler than that. You would just double it.
Oh.
So it would become 0.2, because in this case, you're not getting just one hydroxide. The strontium has one OH group over here and one OH group over here. So it's kind of a twofer. You're getting twice as many of them, twice as many hydroxides as you're getting the strontiums. All right, and you'll see why that's important in just a minute, okay? So let me pause for a second. So when we talk about using the word strong acid or strong base, everything completely dissociates. It goes in one direction, and we've got some concentrations here. Do you want to ask any questions before I do one other thing here, and then we do some practice?
I don't have any questions.
Okay, all right, so now, if I'm not a strong acid or a strong base, then there must be a weak acid and a weak base, all right? And so we'll talk about that in a second. So let me share this with you here. So we can calculate pH of strong acids and strong bases because we know, I'll scoot on down here. All right, so this gets us to the little assignment that I posted for today. So if I say, let's calculate the pH of a 0.28 molar solution of HCl, all right, what we can do is we can say, all right, HCl, that is a strong acid. And so because HCl is going to break apart completely and form H plus and Cl minus, then what we'll say is that if the concentration of HCl is 0.28, then the concentration of H plus is also 0.28, just like we were doing on the previous page. If we think back to how do we calculate pH, we just take the negative log of the concentration of H plus. So negative log concentration of H plus. So I would just literally type this into my calculator. Negative log of 0.28. You put that in your calculator and you get an answer. All right. So finding the pH, if it's a strong acid or a strong base, is actually pretty straightforward. All right. The only tricky part is if you have one of those hydroxides that have 2s on them, and we'll do one of those together in a second. And I'll take a moment. Riley, hello, how are you doing, sir?
Fine, thanks.
Okay, good. We're just running through some notes. I'm recording it, so, and I'll post it here after we get done, so you can capture the first little bit that you missed. Okay, bud?
All right.
All right. All right. So the last little thing is, let me go through one more example problem with you. All right. So let's go ahead and look at this one. So let's see if we wanted to calculate the pH of 0.28 molar solution of this. Some magnesium hydroxide. Magnesium hydroxide, this is going to be one of our strong bases. So we've written the formula for it. All right, it's going to break apart and we're going to get one magnesium ion for every 2 hydroxide ions. And so we sit there and say, okay, if I wanted to know what's the concentration of this guy, if this guy is 0.28 molar, this guy is also going to be 0.28 molar, but because this is twice as much, this is going to get me the concentration of my OH minus. Now, if I'm asking you to find the pH, you're like, well, wait a second. I know the concentration because pH is negative log concentration of H plus. I don't know the concentration of H plus, but I do know the concentration of OH minus. So I can sort of take a little side journey here. I can say, well, wait a second. Why don't I go ahead and find my pOH first? So I'm going to go ahead and say the pOH is the negative log of 0.56. And I'll throw that in my calculator. And that works out to be 0.25. And then I step back and I remember something from the lesson 2 days ago. I remembered this thing where we said that the concentration of H plus times the concentration of OH minus was always equal to 10 to the negative 14th, which allowed us to say that whatever the pH is and the pOH, those have to add up to 14. So if I know what the pOH is, because that's what this is the pOH, all I have to do is say, all right, let's subtract the pOH from 14, and that will give me the pH. So it's a little bit of a tricky problem there. All right, and we're going to practice it here in just a minute. But that's with a strong acid or a strong base. All right. Now, let's see how this might look on sort of the homework assignment sheet. So this is the last thing I'm asking you guys to turn in for the year. So if I look at this, I'm going to put you on the spot here. Riley, does HCl look like an acid or a base? You want to take a stab at that?
I would say an acid.
Because it's got that H out in front. Very good. Yeah. And this was right before you joined in. HCl is a strong acid. So if we see that, in the back of our minds, we know that HCl is always going to break apart into H plus and Cl minus. So if the concentration of this is 0.01, because everything is a 1-to-1 ratio here, the concentration of each of these would be 0.01. So if I want to know the pH, that's the negative log of the concentration of H plus. And I know the concentration of H plus is 0.01. So I'm going to go negative log of 0.01. You put that into your calculator and you get an answer. These guys are all going to be done in the same way because they are all strong acids and strong bases. All right. But then we get to this next problem here, number 6, and it says assume a 5% dissociation. All right, so I want to talk through that real fast and then we're going to be done. So if I'm not a strong acid or a strong base like I am in all of these guys, all right, then I'm a weak acid or a weak base. And instead of, and I'll just use the example here, this is acetic acid. So that H that's hanging out in the front is attached to an acetate ion, C2H3O2. And when we put that in water, all right, it's only going to very slightly break apart into H plus and C2H3O2 minus. In fact, it only does so to about a 5% amount. So mostly the acetic acid just stays together. 5% of it breaks apart. So if this guy has a concentration of 2 molar, all right, and I wanted to know what's the concentration of these guys, all I need to know is what is 5% of my original concentration. So here I would just say, okay, the concentration of this guy would be 2 molar times 5%. Well, if I'm in math class, I'm going to multiply that by 0.05. And 2 times 0.05, last time I checked, I want to say that that's 0.1. So if I wanted to know the pH here, right, that's the negative of the log of the concentration of H plus. And so I would say pH is equal to the negative log of 0.1. And I just put that in my calculator. So anytime you see a percent dissociation, you just have to do a little percentage calculation there. All right, now trying to balance this between going fast, but not going so fast that you don't have any idea what's going on. I'm gonna pause the video here for just a second. All right, so I hope that that has given you enough practice to get a feel for how to handle strong acids and strong bases and weak acids and weak bases and pH calculations.